Hello guys, our topic today is structure 1.1.2 from the IB syllabus. The name is the Kinetic Molecular Theory. Before starting the chemistry, I want to talk a little bit about me. So I currently full-time chemistry teacher in an international school. I am attending every day from Monday to Friday, the international school. I am an IB chemistry examiner with more than 8 years of experience teaching, marking paper 1B, paper 2, paper 3, internal assessment and extended essay. The paper 1B was the last one that I marked. I have more than 10 years of experience as a chemistry teacher and more than 8 years of experience teaching the IB. In total, I could say that I have more than 20 years of experience as a private tutor, chemistry teacher, and I've been teaching online for more than 5 years. Now, I want to talk about the video structure. So first, I will talk about the learning objective. Then I will provide an explanation of the topic using different resources, IB Pearson, IB Oxford, and I will refine my presentation using college books like Cambridge, Brown, and Somdal. And finally, and I could say more importantly for some of you guys, is I will practicing using past papers questions, okay? And I am using a specific section. It means that the question that will show up here in this video is only about the topic that I will explain. So that's making your study of this unit narrower. Let's start it. The kinetic molecular theory is a model to explain physical properties of matter, solid, liquids, and gases, and changes of state. Okay, this is like the introduction of to the changes of state. So you need to be able to distinguish the different states of matters and also use the state symbols like S, L, G, and AQ that showed up in chemical equations. The kinetic molecular theory describes the behavior of matter in terms of particles in constant motion. This is very interesting. And I think that this picture is the best to illustrate the phenomena here. First, we can talk about a solid. If you see in a solid, all the atoms or compounds, we could say the molecules in that case, all the particles are close together. You see, here the solids, there is no movement in the particles. Let's say there is no movement in the particles. I will talk about later about the absolute zero. So imagine that there is no movement of the particles at all. In solids, the movement is negligible. We will talk about that when we are increasing the energy, then the particle of the solid will start to move. So in this graph, you will see the solids, the liquids, they look different. There is not a close packed molecule. And in gases that you will see that the molecules are separated completely. What happened here? Increasing the kinetic energy of the particles. What is the kinetic energy of the particle? The movement of the particles. As I mentioned before, when we have a solid, this is a packed structure and solid. It means that one atom is bonded to another atom. They are like forming a lattice, or if this is a covalent compound, they are forming a structured and rigid version of the state of matter. In that case, we're talking about bonds. So in solids, the atoms are bonded one another. Here we have, when we are increasing the temperature, it means that we are increasing the energy to these particles. They start to move. Because they are a solid, they start to vibrate. There is a vibration of these molecules. They are packed together, but they will start to vibrate. Yes? Now, there is one point when they vibrate a lot that the structure is broken. In that moment, we have the liquid phase, meaning that the rigid solid break down and then we have a liquid. In that case, the atoms are moving a little bit more than in the solid. Is no vibration. Now they experience movement and the movement is higher. The kinetic energy of the particles is increasing. What happens when we increase even the energy more? They start to move these particles and they will overcome the liquid state. Yes? Now we are breaking intermolecular forces that were attracting one compound, one atom, one particle to another is breaking as well. And that's why we have gas state. In gas state is when the particles are separated and they bounce in one another, and the forces are negligible. We say that if we open the closed system that contain a gas, the molecules will escape in different directions, okay? Because there is not an intermolecular force that will capture them. We're talking about ideal gases in this moment, meaning increasing the kinetic energy of the particles. From solid, you apply the energy, then you reach the melting point and you have the liquid, and then if you still continue increasing the energy, then we have the gas state of the molecule or the particle. Okay? This is to explain how the increasing the temperature will increase the kinetic energy of the particle. And then we have the boiling point. And we'll talk about that in the text. Then different states of matter, okay? I am not saying that there are more states of matter, but those are the most important and those the ones that we can evidentiate in our daily life and around us. So we have in solids the particles back. Here we have the interparticle forces, a particle vibrating position, something that I mentioned before. There is no movement of the particles because if they are close together, if they are very close, there is no chance for them to move, you see? So they just start to vibrate. Here they have a fixed shape. So you know that all the solids will have a fixed shape. We cannot change them. And a fixed volume. We cannot change the volume of a solid. In liquid, the particles are more spaced. As I mentioned before, now there are chances for the particles to move a little bit. It's not only vibration, because we are breaking the lattice, we are breaking the solid structure, we have the ability to move a little bit. So the interparticle forces are weaker, particles and slide over each other as well. So because they can move, they have not fixed shape because it's a liquid, you cannot compress a liquid, and they have a fixed volume. We cannot change the volume of you cannot change the volume of a liquid. If you have 1 liter of water, you cannot make 0.8 liters of water out of that applying pressure. Okay, and it's not fixed shape because it will adopt the fate of the container. Yeah. Now the gas particles, they are fully spread out, as I mentioned before, so there is no force. As I mentioned before, the forces are negligible, right? If the forces are negligible, they are still there. Could be some forces there, but we will study that in the initial part. But we say that they have not fixed shape because it's a gas. They will adapt the shape of the container, and they have no fixed volume. Okay, why? Because a gas could be compressed. So if I put a gas in the container and I increase and if I increase the pressure of the container, I can reduce the volume. And if I reduce the volume, so I can change the volume of the gas. Okay, so those are some features that you need to keep in mind as well. Liquids and gases are both referred to as fluids as they have ability to flow. Okay, so remember that this ability to flow allows them to adapt or take the shape of their container. What we mean when we say they are fluids, they can flow as well. Diffusion is another word that you need to keep in mind in this topic. And diffusion would be the process by the particles of a substance spread out more evenly. Okay, so this is diffusion. Another definition is that the particles go from a very concentrated area or a more concentrated area to a low concentrated area. For example, when you have a bottle of perfume, when we spray the perfume, the molecules will spread out in the room, which is containing the air in that specific uh, moment. So always when we talked about diffusion, for example, you see smoke, you see how the smoke will dilute in air. And this is how we talked about diffusion, how this smoke will spread out and you will see how it disappeared over time. This is also another way to visualize this diffusion, okay? Now, here we have a very important equation. This is the equation of the kinetic energy, and this is the one also used in physics. This kinetic energy equals to 1/2 of the mass times the velocity squared. This is the formula that describes the mass and the velocity of the particle and how this is changing. Okay, so here it comes a very familiar situation because you need to either calculate the mass or the velocity in a particular exercise when it comes to diffusion. So that's why we always use the following demonstration to get to one equation that compare two different particles. So we say that particle 1, let's use this blue one here. So we said that of particle 1, let's say mass 1, velocity 1 squared equals to another particle which has mass 2, velocity 2, and is also squared. So we are making this equation. Now, if you see, I can eliminate 1/2 because it's just if I put 2 here, so 2 will be cancelled with 2. So I will get rid of this 2. What I will have here is that the mass of 1, velocity of 1 squared, equals the mass of 2, velocity of 2 squared. Then I will put masses in one side. Mass 1 over mass 2 will be velocity 2, because in this in the right side square, over velocity 1, because it was multiplying, then it will be divided in the other side. I will divide this here, and then we have mass 1 over mass 2 equals, I am getting rid of these squares, so I put that is square root of velocity 2 over velocity 1. So this equation is the one that we use to compare masses and velocities of different particles. Mass 1 comes to the particle 1 and mass 2 particle 2. The particle 2 and velocity 1 to the particle 1. Align the conclusion that is said particles with a smaller mass, and I want to highlight particle with the smaller mass here, therefore diffuse more quickly than those with greater mass at the same temperature. Okay, the smaller, because it's lighter, will move faster, and it makes sense. Yes, when you have two balls, one is heavier than the other one, and you throw them, goes faster. Makes sense. The same path happen with particles, and in this case with diffusion. Here we have the state symbols, which is very important because those are the symbols that you will see in different chemical equations. So as you see, we have sodium plus water produce sodium hydroxide plus hydrogen, but in particular we have solid, liquid, aqueous, and gas. Those are the state symbols we can see in chemical equations. Solutions are more generally mixtures of two components. So we said that we have two components in solutions, and the less abundant is the solute and the more abundant is the solvent. The solute can be solid, but the solvent is generally a liquid. Solutions in water are particularly important, are given the state symbol of aqueous. Very important here. I could say that all the liquids around us are aqueous. Why? Because only water, mercurium, bromide, the pure substances in liquid state, are liquid state. If you see, water is the only one that we put liquid, and as I mentioned, mercurium and bromide are also liquids. Yes, but if you go to the kitchen and you see a solution, this is aqueous. Why is aqueous? Because it's solute and a solvent. There is always one substance dissolved in another substance. Clear example that you can find. You have a beaker. In this beaker you have water, and we have sodium chloride. Once you add the sodium and chloride, then we have the sodium ions and the chlorine ions. These are making this one a solution, and this solution, which we talked about in the video before, is an homogeneous mixture. So this is an example of the solution and the aqueous state. When you have sodium hydroxide, when you have nitric acid, when you have sulfuric acid, when you have different salts, always there will be aqueous. Here we have a summary of the different states of matter. I am taking this picture from Pearson IB. So the change of state, we say that melting is when we have solid to liquid, boiling, liquid to gas. Here we have freezing when it's liquid to solid, condensing when it's gas to liquid. Here we have the reversible equations stating that something that is solid to liquid also could be liquid to solid. It's just decreasing the kinetic energy, as we mentioned in the kinetic theory, right? And here we have that the liquid is also a reversible equation with gas, because also we can increase or decrease the energy, and also the change of matter will change. This is something that I just want to mention, and I want you to keep in mind. We know what is condensation, It's very familiar and very common. What is boiling, evaporation, vaporization? You know what is melting and freezing, but you have to pay particular attention to deposition and sublimation because they are not very common, even though they exist in nature and they are very important. So sublimation is when you have change from solid to gas without passing from liquid state, and deposition is when you have gas to solid without passing for liquid state. They are passing through. We can see this phenomenon. We can see sublimation, for example, in iodine. So you have a piece of iodine and you leave it there, and maybe you increase a little bit the temperature, or maybe with the room temperature, this iodine from solid is not very visible in the picture, but it will be a solid, and this solid becomes a immediately. This is an example of sublimation. For example, if you have performed experiments like this happy little kid using these dry ice carbon dioxide cubes in order to show that he's a very cool scientist. If you see, these cubes of CO2 are changing from solid to liquid. And this is the dry ice that we know as well and we can buy in different places. Very easy to acquire. Here we have the deposition. If you see in nature, this is very common in crops when the gas, the water gas, becomes solid straight away because the low temperatures. So here we have of a deposition. Something important to mention as well is that liquid can change to gas by two processes. Okay, one is evaporation and the other is boiling. So we said that boiling occurs at a fixed temperature. So the boiling point of ethanol is 79 Celsius degrees. A boiling point of water is 100 Celsius degrees, depending on the height. That is the general rule of the boiling point of water. Fixed temperature for a given pressure. Now, evaporation occurs only at the surface and take place over a range of temperatures below the boiling point. So below the boiling point, just very close to this lower boiling point, some molecules in the surface will start to change from liquid to a gas. But we say that this is an evaporation because it's only the molecules in the surface. Yes. So here I have this picture of this application of the gas. Here I wanted to mention that the pressure of this gas is very high, and that's because it's compressed to this pressure. Is liquefied in this moment. When we have a pipe of oxygen or a pipe of methane or a pipe of a gas, you feel that this is like a liquid. But as soon as you open the container, it goes as a gas because now it's pressurized. It's not exerting that pressure, and that's why it is free, and the molecules are diffusing very fast. And because the molecules are diffusing, here we take advantage of this, and then you can use this as an energy. So I just wanted to show this example. Okay, guys, now we get to this part of the video when we have the past paper exercises for this topic. They look very easy, but still you need to practice what you learned today. Okay, so this is a past paper. So this exercise was taken from the International Baccalaureate Organization, and this is one of them. Which equation represented the position of iodine? Please stop, try to solve it, and then continue the video and you will see the answer. Remember that the position is a particular change that we talked about, deposition and sublimation. Those are the weirdest ones. Here we have the first one, gas to liquid, condensation, gas to solid straight away without passing from liquid, deposition. Okay, so that will be the correct answer. You don't need to spend more time reading the other ones, even though you can check them. Liquid to gas, that would be boiling. Yes, evaporation. And then we have solid to gas, which is the opposite to deposition. That will be sublimation. Okay, so the correct answer will be B. Now here we have another question. What is the change of state for a gas to a solid? So exactly the inverse. Gas to a solid. So we said condensation. No, condensation will be from gas to liquid. Deposition will be from gas to solid. Yes, so it's deposition. It's not rocket science. It's very easy. Freezing, you know that is from liquid to solid. And sublimation will be from a solid to a gas in one way. Okay, so in this case, we have deposition as our answer. Here we have some exercise that I want you to practice from the book. Please stop the video, try to solve them, try to practice what we learned today, and this will be very useful for your exam, okay? If you know how to approach and solve the questions that I showing you here in these videos, then I am totally sure that you will be able to uh, face one of these questions in a paper. Here we have 10, 11, and 12. Stop there, try to solve 10 minutes, and then you check the MR scheme here that I am sharing with you. Okay, if you got to this point without solving, then just stop, go back to exercise 7, 8, 9, and then 10, 11, and 12. Try to solve them. If you don't know how to solve them, here we have the MAR scheme, but the idea is that you will practice before and then you will see if your answers are correct. If you definitely think that answers don't match the questions, please let me know in the comments and I will help you and I will support. I will provide more and deeper explanation about this. Okay, guys? The topic for today. Have a good one. See you in the next video.